So now I want to simulate this advanced weighted summer circuit with the values of the resistors we have determined. I want to simulate this in the simulation to see if it's true. So we have, as in the prompt, it said this relationship from Vout for the inputs. So I'm just going to arbitrarily pick some values for V1, V2, and V3. I'll do 0.1 for V1 and 0.2 volts for V2 and 0.3 volts for V3. I just picked this arbitrarily, and then in that case Vout is equal to 2 times 0.1 plus 1 times 0.2 minus 4 times 0.3. Then Vout is equal to 0.2 plus 0.2 minus 1.2. Vout in this case is equal to negative 0.8. And to continue on, let's pick another example, arbitrary values. I'm going to keep V1 also equal to 0.1 volts and V2 also 0.2 volts, but this time I will make V3 negative 0.3 volts, and the reason is because the negative sign can force this value go to positive. So in this case Vout is equal to 2 times, so it's the same, but it's 0.4. Okay, let's just write 0.2 times 0.1 plus 0.2. This time it's 4 times negative 0.3. So this is Vout is equal to 0.4. Minus a negative is plus, and there's 1.2. So then we can expect Vout is equal to 1.6. So we'll test for these two cases. So now we have the simulation for this advanced weighted summer circuit for the simulation software called Psim. And so I have recreated the circuit topology here. And I have used the default, which is like, basically it's the ideal op-amp, and I have selected the power supplies for the op-amp to be 5 and negative 5 volts on each rail, and 5 and negative 5. And we'll test for the first case when we arbitrarily picked V1 to be 0.1 and V2 to be 0.2 and V3 to be 0.3. So we calculated that the output should be negative 0.8. So the output's negative 0.8. Likewise, in the second case, when we make this negative 0.3, we expect the output to be 1.6. So 1.6 on the output. Okay, so this behaves as expected. Now, one thing we can demonstrate is, let's divide all the resistors by 1000. And because the summation property of the weighted summer circuit is dependent on the resistor ratios, so dividing all the resistors by 1000, it should not have any change to the output, so it should still be 1.6 volts. So it is. And so let me just bring back all the values from previously. Okay, now what happens if we times all the inputs by 10? So now this is 1 volt, and now this becomes 2 volts, and then this becomes, well, let's just do 3 volts. So it would go from negative 0.8 volts to negative 8 volts. So the new output should be negative 8 volts, right? The thing is, that will not be the case. And if we measure the output, it would be negative 5 volts. So yeah, it's negative 5. And the reason is because our op amps are the power supply limits us to be between 5 and negative 5 volts of output swing. So, but since our output is negative 8, if I increase this to between 10 and negative 10 power supplies, then now we can achieve the output of 8 volts. So, negative 8 volts output. And likewise, we do that for the other case when this was negative 3. So this should be 16 volt output. No, because 16 volts is beyond the range of the power supply here. So it would saturate at 10 volts. So it saturates at 10 volts. So we can make this like 20 volts swing to negative 20 volt swing. Yeah, now we get 16. Now one thing is, we don't have to have. So actually, let's just bring this back to that positive 3 and then this to be 10 and negative 10. So, right, so this would be 8 volts, right? Negative 8 volts, right? So one thing is we don't have to keep the power supply the same for both. What we can do is we can take a voltage probe and we put it here. And I'll call this Vx for the test voltage. Then if I simulate, so I'm measuring the value of the output of the first stage. So if I get that value, we can see in the red trace the value of the first stage output is negative 4. So that sits between the default value of the original power supply between 5 and negative 5. And so output should still be negative 8 volts. So yeah, it's still negative 8 volts. So we don't need to necessarily have both op amps having the same power supply. And the reason why I want to keep it low is because 10 to negative 10 is not a realistic value for the op amp. A realistic value is like 5 and negative 5. So you may be wondering, well, in that case, because the output is negative 8, can we maintain the same 10 volts output swing but just change this to go to like 10, but then the bottom is 0? Can we do this? And the answer is no, because this op amp does not behave symmetrically like this. When you give it non-symmetric power supply like this, this op amp will not work. In fact, the output would be stuck at 0. So yeah, the output's stuck at 0. But one thing we can do is we can give the negative power supply negative 10 and the positive power supply 0. And will this achieve it? Well, let's take a look and simulate. And yes, it does. So now our output is negative 4. So basically what it's saying is, because a 10 volt swing is a more realistic value. So what we can do is maintain the same 10 volt swing, but just shift everything away. So now we're going between 0 and negative 10. So when our output is at, the green trace is at negative 8, what that means is that the output has to sit between the upper bound and the lower bound. These are our power supplies. If in this case it's an ideal op amp, which means that output can swing rail to rail. And so in this case, we can maintain the same more realistic value for the power supply and yet still get our desirable output of negative 8.